All right, so the last part of this chapter, which is not chapter 11 in our book, it's chapter 5, is periodic trends. So we've seen this before in the very beginning of the course where we talked about the difference between metals and non-metals and metalloids. All right, and so we said that metals are, they're shiny, and they conduct, and they're flexible, all those parameters. Whereas nonmetals are exactly the opposite. They're dull, they're insulators, etc. So there's actually a trend which is the same, it's a synonym for pattern on the periodic table. For example, if I'm comparing lithium and neon, lithium is a very metallic element, whereas neon is a non-metal, so we would say it has no metallic character. So going from the left towards the right, we increase in non-metal character, but going from the right to the left, like this, we increase metallic character. Going up and down, it's kind of similar. So metallic character is, in group 1, is related to how quickly they react. And we saw that like lithium has a pretty small reaction, but rubidium was pretty impressive. So that means as we go down the row, the metallic character is increasing. You can summarize this with little arrows. Metallic character pointing to the bottom left, and non-metallic pointing to the top right. So what that means for us is that helium is the most non-metal element on the periodic table. It does not mean it doesn't like good rock and roll. It just means that it is not an insulator, it's very dull, it has all of those non-metal characters that we outlined in the beginning of the term. On the other hand, on the other side actually, all the way on the opposite side of the periodic table, we have francium. Francium is the most metallic element in the periodic table. It means it's the most conductive, it's the shiniest, it's the best metal there is. Well, maybe not best, but it's definitely the most reactive metal that there is because it's at the bottom of group 1, and group 1 is already a reactive group, so you can imagine that the explosion francium would create would be quite impressive. Okay, so for the rest of the trends, we need to have some definitions. So atomic radius is based on the distance between the center of an atom, which is the nucleus, out to the edge. And that space is mostly occupied by electrons. Okay, we also need to define ionization energy. So the word ionization means to ionize. To ionize. And ionize means move electrons. So ionization energy is literally the amount of energy to remove an electron. Okay. Electron affinity, which affinity means how much you like something. So I have a strong affinity for chemistry, let's say. Some days. Today I do. So if I had a strong affinity for electrons, it means I really like electrons. So you can measure how much an atom or an element wants electrons. Some atoms really want them. Other atoms really don't want them. They give them up very, very easily. Okay? So a synonym for electron affinity is what we call electronegativity. But it means the same thing. How much does an atom want to have an electron? Okay. So the next trend we're going to look at is the atomic radius, or size of an atom. So if we look here across this period, period 2, compare, say, lithium and neon, which are on opposite sides. Which one's bigger? Well, clearly lithium. So our size gets bigger going from the right-hand side to the left. So this is small, and this is big. Now, that doesn't really make much sense to us because we know that as we go up the periodic table, up in periodic number, atoms are actually getting more electrons. But we're going to learn about why they shrink when we add more electrons in just a minute. So just hang tight on that one. Up and down makes a lot more sense because we know we're adding electron shells as we go down. So here's the 2s, here's 3s, 4s. It makes sense that those get bigger as we go down. The reason for that is we're adding more energy, we're adding more shells. So the atom has to get bigger. Okay, so to explain the trend going across the periodic table where it gets, so here's our little tiny periodic table. The trend in atomic size is that it's small on the right and it gets bigger on the left. That's weird, again, because we have more electrons on the right, so you might expect that it would get bigger as we went from the left to the right, but it doesn't. Okay, here's why. We call this effective nuclear charge. So, if I have one electron that's really close to the nucleus, like this picture here, compared with one electron really far from the nucleus, which one has a stronger attraction? The answer is the top one. That makes some sense. We know that positive and negative charges are more attracted to each other when they get close together. It's like the magnets idea. Like if you have a magnet on your refrigerator and you're holding it across the room, it doesn't feel attraction. But if you hold the magnet a couple of inches from the fridge, it will suddenly zoom right to the fridge and connect to it. The same thing applies to electrons. When the electron is really close to the nucleus, it feels a stronger attraction. Okay, so the electrons in the outer valence shell are less attracted to the nucleus than the inner electrons are. Okay? Now, if I have a situation where I've got a lot of electrons on the top versus the one electron on the bottom, that complicates things a bit. These electrons that are inside, the core electrons here, these electrons repel each other. They don't actually want to be close together. They do want to be close to the nucleus, though, so they don't go flying off into space. So the core electrons are repelling each other and repelling the valence electrons, but they want to be there because the protons in the nucleus are super attractive. But because these inner electrons are closer to the nucleus, they kind of screen everything from the outer electrons. So these outer electrons don't feel as much attraction to the nucleus as they would if those core electrons were not there. So what that means is these outer electrons are allowed to slide away a little bit. That makes the atom bigger than it really ought to be. So the effective nuclear charge is kind of caused by the core electrons screening the outer electrons, and so the outer ones can pull away more than they otherwise would. As we are adding more electrons from the left to the right, so that's more electrons, we are also adding more protons from left to right. That means that there is more positive charge on the nucleus, so those core electrons are even more strongly attracted than they would have been if we didn't add any extra protons. So those core electrons get hugged in nice and close, but the outer electrons tend to drift away a little bit. That makes these ones, if there are outer electrons on the left side, that makes these ones not held as close to the nucleus as the core electrons are. If all we have is a full shell, so we're the noble gases column, everything gets hugged really, really tight because it's all paired up and everything is really stable. Okay, so this is the reason that the atomic radius trend is kind of backwards from what we thought. It gets smaller going from the right to the left, because there's a lot of protons in the nucleus over here, and that has a very strong pull on all of the electrons, even the most outer electrons. Whereas on this side, we don't have as favorable of a balance of protons with electrons. Okay, so let's review. Again, this is chapter 5. The first trend to review is metallic character. So you can ask yourself, okay, self, which element is the most metallic? And the answer to that is francium. Then you might say, okay, self, what is the least metallic? And the answer there is helium. Okay, so we can draw our arrows pointing towards francium and towards helium towards francium for metallic, towards helium for non-metallic. And then you might ask yourself, okay, self, what atom is the biggest one in the periodic table? And so we said that things on the right are smaller than things on the left, and we said that things on the top are smaller than things on the bottom. So that means francium is the biggest element on the periodic table. Helium is the littlest element. Oops, I went too far. The littlest element on the periodic table. I can't write the word little, so you're just going to have to fill it in on your notes. So we could summarize that by using arrows that point from little to big, which means they're going to point towards francium and away from helium. Okay. The next trend we got to learn about is ionization energy. We saw those reactions between the group 1 elements like sodium, where it goes from solid to the ion sodium by producing or releasing one electron. While that's happening, the chlorine gas in this reaction is going to go absorb those electrons. So each chlorine gets one electron added to it, which means these two chlorine, the subscripts mean 2 there, each need 2 total electrons. And when they absorb an electron, they don't have the same number of protons and electrons anymore. Now each one of them has an extra electron. We show that extra electron by writing a negative sign. Why is it negative, you ask? I'm glad you asked that question. The reason it's negative is because electrons are negative. So if we are adding a negative charge to a neutral element, we obtain a negatively charged ion. Okay, over here, back to the sodium. This is the reaction that happens when we steal the electron from sodium. It requires energy to steal an electron from any element because you are breaking the attraction between the protons and the electrons. For our purposes, we're going to be thinking about taking only one electron from each element, but it is possible to change to steal more than that. You have to steal the first one, and then you can have the second one and the third one and on like that. But for our purposes, we're just going to think about the first one. Now this reaction that makes sodium and chlorine together, sodium chloride, which is salt. So NaCl is table salt. There's going to be a link to a video showing you this reaction in Top Hat, so you should definitely check it out. When this reaction happens, it produces a ton of heat, lots of heat. You can see it. That means that the sodium in this reaction really wanted to get rid of its electron. It still costs a little energy to do it, but it really wants to get rid of it. Kind of like cleaning house in the spring, right? You start dumping things out. Costs energy, but you feel much better afterwards. Chlorine, on the other hand, is not so good at dumping electrons. Chlorine is a hoarder. It wants to take electrons from everybody that it can. So when you put chlorine and sodium together, it's going to steal 2 different electrons, one from one atom of sodium and another from a different atom. So trying to take an electron from a hoarder is really difficult. That means it has a high energy. And sodium is on this side of the periodic table, and chlorine is on this side. So we would be able to summarize this by saying that it's relatively easy to take an electron, meaning low energy. Oh, that says low. But from chlorine, it is not easy at all. It's very difficult. Costs energy.